Hey everyone, welcome to this explainer. Look, if you're a college student staring down the barrel of a basic electrical engineering course right now, you probably already know how fast things can get, well, completely overwhelming. But seriously, don't worry. Today, we're going to calmly break down the foundational engines that power literally every electrical network you'll ever encounter: voltage and current sources.
So, take a deep breath. If those massive webs of lines, nodes, and weird symbols on your homework look like an alien language right now, it's totally normal. Honestly, we've all been there. Today, we're not going to stress over solving some massive multi-loop nightmare. Instead, we're just going to slow things down. We're going to look at the heartbeat of these circuits, just one simple piece at a time. By the end of this, you'll be able to glance at those intimidating diagrams and instantly spot the exact parts that bring the whole thing to life.
All right, let's jump straight into section 1, the heart of the circuit.
Okay, to make sense of any electrical diagram, let's just start by organizing the chaos. We'll separate the components into two main camps. First up, the active elements, or as you'll usually hear them called, sources. Think of an active element as the beating heart of your circuit. It's the battery in your smartphone, the massive generator at a power plant, or, the solar panel on your roof. These components are constantly pumping energy into the system, pushing electrons around and quite literally bringing the entire network to life. Without them, well, your circuit is really just a collection of dead metal.
On the flip side, we've got our passive elements. These are things like your resistors, inductors, and capacitors. Now, they don't generate any power of their own. Instead, they just absorb the energy from those active sources. You can kind of think of them as the peaceful pathways and the natural obstacles within the network. They either dissipate energy as heat, kind of like a toaster does, or they store it temporarily. But the key here is that they rely entirely on those active elements to actually do anything meaningful.
Moving right along to section 2, voltage and current sources. So now that we know active elements are energy suppliers, let's gently examine the two main types you're going to encounter all the time in your studies and, on your exams. You'll typically see these drawn as circular symbols. Those represent what we call independent sources. You can think of them as steady, super reliable engines that just do their job, totally ignoring whatever else is happening out there in the rest of the circuit. Whether you hook up a tiny little LED or a massive industrial motor to them, these independent sources are going to stubbornly try to push out the exact same amount of energy they were designed to give.
And this brings us to our two main flavors, voltage and current. An independent voltage source holds its voltage, which is basically its electrical pressure, perfectly steady, regardless of how much current is being drawn from it. Imagine a water pump that keeps the exact same water pressure going, no matter how many faucets you open in the house. On the other hand, an independent current source maintains a continuous, unwavering flow of current, completely ignoring the voltage across its terminals. That's like a pump forcing exactly 5 gallons a minute through a pipe, whether that pipe gets super wide or incredibly narrow.
But not all sources are that stubborn and independent. Actually, sometimes the source's output relies entirely on what's happening in another part of the network. We call these dependent sources, and you'll usually see them drawn as diamond symbols instead of circles. There are 4 types of these, basically depending on whether they output voltage or current and whether they're controlled by a voltage or current somewhere else. Honestly, just think of them like a smart valve. The flow happening right here is automatically adjusted based on a sensor reading way over there.
All right, let's head into section 3, perfect versus real world. So far, we've been talking about this perfect, theoretical textbook realm where sources just work flawlessly forever. But reality is a bit messier. An ideal source on a graph holds a perfect horizontal line of voltage. It literally never wavers, even if you draw infinite current from it. But for a practical source, as you draw more current, the voltage slowly starts to sag. This is real life. If you've ever noticed your car's headlights dimming slightly right when you crank the engine, yeah, you've witnessed this exact practical voltage drop happening in real time.
So how do we actually draw this real-world imperfection on paper? Well, this gentle drop-off happens because a real-life battery, a practical voltage source, isn't just a magical well of infinite energy. It has its own internal resistance built right into its physical materials. To model this, we just draw an ideal voltage source sitting in series with a tiny resistor, which we call source resistance. This little internal resistor quietly eats up some of the battery's own energy before it can even make it out to the rest of your circuit. And it's a very similar story for a practical current source. It's not perfect either. To show this on our diagrams, we model it with an ideal current source in parallel with a source resistance. This parallel pathway is a great way to visualize how a little bit of the current inevitably leaks away internally, instead of flowing out to the main circuit where we actually want it to do work. It's just a really simple, elegant way to make our textbook math match up with messy reality. Okay, on to Section 4, changing forms simply.
Picture this. You're sitting in an exam. You get the whole sources concept, but the math on the page looks like an absolute nightmare. But what if you could just change a voltage source into a current source to make the whole thing calmer and easier to solve? Well, this brings us to an incredibly powerful trick called source transformation. The big takeaway here is that you're actually not stuck with the circuit exactly the way your professor drew it. Source transformation lets you fluidly swap between a voltage source and a current source without breaking a single rule, letting you simplify those stressful networks into something way more manageable. By following 3 really easy steps, you can start treating circuit analysis more like a relaxing puzzle. First, just find a voltage source sitting in series with a resistor. Second, you literally erase it and redraw it as a current source sitting in parallel with that exact same resistor. And third, just use our old friend Ohm's law to calculate the new value. It's that simple. You're just shifting pieces around until the math practically solves itself. Mathematically speaking, a voltage source in series with a resistor is exactly identical to a current source in parallel with that very same resistor. You can transform it from a voltage setup to a current setup or flip it right back. By doing this little swap, you might suddenly find that 2 resistors that were awkwardly placed are now neatly sitting in parallel and can be combined in seconds. Seriously, it's a massive stress reliever when you're stuck on a problem.
As we wrap up this explainer, I really want you to hold on to this concept. Beneath all those dense equations, the terrifying nodal analysis, and the endless branching wires, every single intimidating circuit is just a combination of simple active hearts and passive pathways. Once you learn to spot those independent sources, you've found the pulse of the problem.
Look, mastering these fundamentals is a journey. It takes patience and it definitely takes practice. If you don't get it perfectly the very first time, give yourself some grace. You've absolutely got this. Just keep looking for the heartbeat of the circuit and the rest will naturally flow from there. So I'll leave you with this little thought. Next time you look at a massive complex circuit board, maybe even the one inside the computer or phone you're using right now, ask yourself, where is the heartbeat and how is it transforming to bring that entire machine to life?